2, 1, so Newton's law of gravity. So welcome in, most likely your introductory physics course. So what is this Newton's law of gravity? So what is really interesting about all of the laws that Newton has had, so, you know, kind of Newton's first law, Newton's second law, Newton's third law, and then really this kind of almost is like a Newton's fourth law, but, you know, it typically may be just called the law of gravity, and it wasn't grouped into those 3 particular laws. So Newton has done quite a lot of things, and one thing that he has noticed and actually has come up with, and it's always through some form of experimentations, which is really nice in physics, is the fact that there is basically a force between any 2 objects that carry some kind of a mass. Now, you know, why does this force come into play is not really an interest, although, you know, it would be wonderful to be able to answer, you know, all of the different whys, but we certainly want to be able to have laws on observable things. So like what happens, okay, if we're going to be observing items. So I just want to be able to explain this particular law here and just let you know, just so that you get a gist of it. It's not very difficult, and typically you just get fed the actual formula for the law, and then you just keep using it, right? But I want to give you a little bit of a perspective on these. So what was, you know, Newton kind of up to? So imagine that you would remove everything, and all you would have is basically you would place one object and then another object. And those were the only 2 objects that you had. There was nothing else around. Now, obviously, that's very difficult to do, okay, to create some kind of a vacuum and only have 2 objects, but let's assume that that's what we have. And this observation is the fact that if you do have 2 objects and one carries a mass, okay, so let's say we have mass m1, and the other one carries a mass, and this is maybe mass m2. Now I have drawn these as circles, right, or spheres, if you were thinking of 3 dimensions, but it doesn't matter what actual shape that they have, but they do contain some mass. And what has been observed is that if you do have these 2 particular objects, what happens is that there is a force of attraction between them. So basically these 2 objects get pulled in together. So they would just kind of start to come together. Now, what is that force, right? So if you remember, you know, forces are some kind of a push or a pull. So it doesn't matter if, you know, if you call these pushes or pulls, right? Or I guess they're getting pulled in together, so they're sucked in. So typically we would say that it's an attractive force, so they're just being attracted to each other, right? So they're just kind of pushed in together. So if you have these 2 objects, what has been observed is the fact that you can take the 2 objects and you can create and see that there is some kind of a force. Now these forces are equivalent. So one is acting on one object and then one is acting on the other object, and they are equivalent. So that's what you have. Now the question mark is, you know, what is this particular force? So we know that they're basically the same. This is what we observe. But what is it? You know, can we actually measure this particular force? And the answer is yes, we can measure, okay, the actual force that we have. So this is, okay, if you have these particular 2 objects, M1 and M2, what it turns out to be that your actual force, okay, that you have present. Now I'm going to say that this is the force that 1 exerts, okay, on object number 2. And you can certainly do that. And you can say that this is, if you were doing it, except that they would be in opposite directions, right? So this is almost like your Newton's third law, action and reaction. So if one is exerting one force on the other one, okay, there has to be a balancing force, and that is certainly true. So you would have a force, okay, on 2 from 1, but it would just be in the opposite direction, where the negative just means it's opposite. So now the magnitude of this actual force, so if you were calculating the magnitude, you know, I can drop the 1 and 2, and let's assume that we're only considering the actual magnitude. So we know that the direction is going to be, okay, in the actual attractive wave, so from one to the other, as you can see here. So this is the force that we have. The direction is presented there. But now we want to be able to know what that magnitude is. So that magnitude turns out to be, okay, first thing is that it's going to have an impact on the fact that you have two of your forces, or two of your masses, my apologies. So you have the mass M1 and mass M2, and it turns out that it's going to be the multiplication of these two particular masses. So this force is proportional to the actual masses of the objects that you have. So the bigger the mass, the bigger the force. The smaller the mass, the smaller the force. So that is just a proportional item. Now, what else has been actually observed is that these two particular objects, they can be close together or they can be far apart, right? So just how far apart are these objects, and then how do we measure that throughout? So I'm going to just remove these forces now within here, and I'm just going to concentrate that it turns out that your actual force is also, okay, proportional to the distance between the two. But it's not directly proportional, it's actually inversely proportional. Now, what do we mean by inversely proportional? It means that the bigger the distance apart that you have, okay, then the force actually goes down. So, as your distance between the two of the masses goes up, your force comes down, and that's called inversely proportional. Okay, so that's something that you would have in there. And I can put up a link, okay, up above there, okay, that may discuss for you, okay, the proportionality, if you like. This kind of goes back towards math. But so now this inversely proportional item, okay, what has been observed is that it turns out that it's going to be in the denominator. Now, we typically will take, and what this is referring to, is that if you take the center, right, of your actual object, so it's very convenient if they're actual circles, then you can, take the center directly, and the actual distance in between, okay, that you have, okay, so this distance, okay, so this is the actual distance. And sometimes, very often this would be referred to as the kind of the radius in between there. But, okay, so that's why I wrote a little r there. But don't be shocked, instead of your r that you have, you might be referring to the actual distance in between, right? So this is the distance between the two objects. And as these two objects kind of move further apart, you can see that the distance would get bigger. And as they get closer together, the distance would get smaller. And therefore, if the distance gets smaller, the force is going to go up because of the fact that this is in the denominator. Now, through observation, the actual, how it's inversely proportional, it is not just to the distance, it's actually the distance squared. So this is what you would have. So that is, it's actually squared to the distance. So this is what you would have now. So again, it is proportional to the mass. So the force is proportional to the mass, but it is inversely proportional to the distance squared. Now, this is almost getting us there. We can almost put an equal sign here, but not exactly. And what has been observed is that right in front here, okay, in order to make this equality, or at least really close to an equality, is that it has turned out to be that we have a constant. And this particular constant is called the gravitational constant. Okay, so constant of gravity. Okay, and we're going to be labeling it as a capital G. So this is what you will see in various formulas. And this particular capital G is just a constant, so that means it is fixed. So no matter what two masses you're dealing with, that constant is the same, and this has been shown through experimentation. And it is equal to 6.67 times 10 to the negative 11. So this is where our scientific notation comes into play. So it's a very tiny constant. So as you can see there, that the two masses that you have, if they're small masses, right, even if they're 1 kilogram, then you can see there that because of that constant, it's going to be a very tiny force. And of course, please keep in mind that you are thinking about two objects with nothing else that is interacting with them. Because as soon as you put other objects around, now this particular gravitational, so the law of gravity, starts acting between all the actual objects. And then the forces between them, as you start putting more and more of these objects side by side or near each other, they're going to cancel each other off. So that's why you don't see, one object. If I would take, one ball and then I would take another ball, why aren't they sliding towards each other if this force of gravity, prevails? Well, keep in mind that there's all other types of forces around. And the bigger the objects they are, the bigger attractive force that they will provide with this gravity. And the biggest thing near the Earth's surface is, of course, the Earth itself, which is enormous in size in comparison to all of us. So all of those little forces of attraction between smaller items is going to just get canceled off. It's going to get eaten out by a much bigger force, and that is the force which is coming from Earth itself. And that is, the attractive force, indeed, that takes over. And this is where we have our constant G, which is approximately 9.8 meters per second squared. And this you may remember from kinematics, right? So this 9.8 meters per second squared actually does come from this law of gravity in here, so Newton's law, where one of the masses is Earth itself. So that's what you have. And if you wanted to be able to actually measure, so as you were calculating and you've ran in and you said, the force of gravity, or sometimes you might be calling it weight, and it was equal to whatever mass you have times gravity, really what you are doing is you're taking this equation, in here, and you're finding this out. So that G is nothing else. So if you would rewrite this, as a whole, this particular G is going to be this capital G. It's going to be, now I'm going to capitalize this, it's going to be the mass of the Earth that you have, and then it's going to be divided by the actual distance in between. Now, this is why we typically might just put it as R, and maybe that's what I will do instead of using the distance D between two objects. R would represent the actual center of the Earth, and wherever the object is, and this would have been squared. And as you can see there, so this M right here is the other object. And if you would bring it back into the equation, so if you bring it back into here, you would just get capital G, 1m, which is the mass of the object you're interested in. Capital M, let's make that the mass of the Earth divided by the radius squared. And now you have your actual force of gravity between an object and the Earth itself, where this as a whole is going to be, your gravity pull that you have on every single kilogram, of mass. So please remember that the masses are in kilograms and SI units. The actual radius, or the distance between the objects, is going to be in meters. And now the question may arise, what is this constant, right? So this particular constant, how did we find it? Well, we found it through experimentation, so the scientific method where we repeat constantly experiments and so on. Now we have really good tools to do that, to find out that this constant is indeed this tiny item. And its actual units, and this is a test for yourself, because ultimately what you want is you want the force, of this gravity to be in newtons, and in order for that to hold true, so as you can see there, if that has to be true, then this constant and the units of this have to align so that in this equation, everything would cancel out the units. Now, if I go back here in units and I start thinking about mass is in kilograms, notice the other mass is going to be in kilograms, so this is going to be kilograms squared, divided by the distance or the radius between the two objects is going to be in meters. That's the unit. Notice it is meters squared because of the fact that this is squared right there. And now, if you want to have as a result, so right here, this is supposed to be in newtons, so your result has to be newtons. So in terms of your units, that will now tell you can solve for what the actual units for that G is. And then I would encourage you, so you can put a little question mark in here, okay, and you can put in those units, right? So if you want newtons out, that means the kilograms would have to cancel. So here, if I'm putting in the units, so kilograms would have to be in the denominator of this right there. The meters square would have to be in the numerator, so that would cancel those. And then this would have to be also in newtons right there. So that way, if you substitute this back into here, you indeed are going to get newtons out. So those would be the units of this constant that you have. And all of that has been done through experimentation. So for this acts for any two objects. This isn't just between the Earth and you or any other object. This is between any two objects that carry a mass. So this is between the sun and the Earth, the actual Earth and the moon, any other planet, or any other smaller objects. Now, if you took a look at this, so in terms of this particular equation that you would have, okay, you can certainly plot it, and then you would notice that the only thing that really changes if you have two objects, their mass won't change. The G, capital G, the constant, because it's constant, that will not change. But the actual distances between objects will. And the further the distances are, very quickly that force, that attraction force starts to fall off. It gets smaller and smaller. That's why if you get further and further away from the Earth, right, as you keep going, the force, the attraction force from the Earth itself is going to be less and less and less. Okay, and you can actually pull yourself out, and then you'll notice that this, okay, 9.8 meters per second squared is very valid when we're very close to the Earth. But as you get further and further away from the Earth, this will indeed get smaller and smaller. Okay, so that's how it will work. Now, I have actually done this in terms of a Desmos representation here. So if you've never run into Desmos in terms of graphing, you should get probably acquainted with some kind of a graphing tool. So what I've done is, notice I've put G here on the left. So that's my constant. I put the mass of the Earth. Notice it's enormous. Okay, so that particular mass of the Earth is enormous. I put the radius, of the Earth. Okay, it's not exactly spherical. So it is, it's typically around the equator just because of the spinning motion. So it's a little bit almost like an ellipse. So it's a little bit, thicker in terms of the equator, and it gets a little bit less at the upper ends at the poles. But in any case, on average, it's approximately 6,371 kilometers. It's quite a lot. And if you change that to meters, that's why I multiplied it by 1,000. And now if you would put in this equation in here, so notice if you wanted to know what the force is, I'll put R in terms of the radius right there. So that's going to be, here's your G that you have. Here is basically the masses that you would have in here. So now I can, put this as I like. So let's say M is going to be one mass. I'm going to put the second M. So maybe what I'll do is M1. And then this will be M2. This would be two objects, that you would have divided by the radius, and this would be squared. This is the distance between those two objects. If I put that in here, now this is only 1 kilogram, so maybe I'll put 1,000 kilograms for each of the items, and then you will see that you will have your relationship being plotted out. Now the radius obviously cannot be negative, so maybe we should change this, so R should be greater than 0. And notice that this is the force that you would have. So when the two objects are very close together, notice that the force kind of blows up. It's really large. So notice if I zoom in here, so you'll see that the force gets really, really big as things get closer and closer together. But as they get further and further apart, you can see there, and it doesn't take much, that it very quickly starts to drop off because you have your radius squared. So you're squaring the distance, as you're going through, and then it very quickly falls off, basically almost to 0. That's why you see, no objects are going to be kind of just being pulled in together if they're very tiny, or it would take a long time. And again, it goes back on the Earth actually dominating, throughout. right? So the Earth, its mass as a whole is going to dominate. So any two objects won't really get close together as much. Now, to just let you in so that you can see, where this gravity G 9.8 or approximately 9.8 comes from. So I mentioned to you right there. So if I go back in here and I take out our notes, okay, so you'll notice that right here, I pointed out this was, okay, the actual G, right? Okay, the force of gravity, okay, that we would have, and it would be in terms of an acceleration. This is just now on 1 kilogram, so that's why that would be as an acceleration. Okay, so within here, and if I would plug this in, notice if I take G, okay, I multiply it by the mass of the Earth, right? So I'm going to just write this out in there. So I have written them in, and then, so my apologies there. So if I now take this, and I now divide this whole thing, let's see if it lets me do that. Maybe I'll do it here. So divided by, now this is the radius squared. This is going to be the radius of the Earth. Okay, radius of the Earth. And this would be squared. Notice what item it gives me, or at least what number. 9.81395, so on. So basically the force on 1 kilogram, okay, indeed is 9.81 or just 9.8 as we approximate it. And that does come from this, okay? So Newton's law of gravity. So I hope that this gives you a sense. It gives you a graphical viewpoint, how you can see the force actually quickly kind of starts to drop off. If you're dealing with the Earth or any other planets, okay, well, then the actual forces that you have in between them, okay, are coming into play. Now, you might start asking, well, if you have these forces between planets, why aren't they just coming in closer and closer and eventually just crashing? Because if these are attractive forces, what's keeping it there? Now, please don't forget that the Earth is rotating around the sun. So it is moving, and it is moving approximately at a constant speed. And that might bring you back to centripetal acceleration. So yes, the force of attraction between the sun and the Earth tries to pull these things together, but because the Earth is actually moving, okay, it keeps spinning it around, and that gravity, okay, is actually holding it in orbit around there, right? So remember that the actual centripetal force, I can put up a link up above there for you, is what is keeping the Earth in rotation, okay? So that's what happens because it does have an actual speed. In any case, I don't want to go in that direction here. I just wanted to be able to present to you the force, okay, of gravity, or that's coming from the law of gravity from Newton. So you can now take this equation, you can now use it for any two masses and find out exactly what the forces might be. Thanks for watching. See you in a future video. Bye, everybody.